All right. Welcome to August. We'll just, so you have some basic introduction, brief introduction to arithmetic and geometric sequences, which are 5.1 and 5.2. So the first thing I want to do is remind you of our four representations of mathematical ideas. And arithmetic and geometric sequences are basically a way to relate symbolic and numeric representations of two different types of functions. Arithmetic sequences are linear functions, and geometric sequences are exponential functions in numeric form using numbers. So, for example, if I take an arithmetic sequence and it looks like this. X is 1, 2, 3, and 4. Y is 9, 12, 15, and 8. This right here, the Y's, this is the arithmetic sequence. Nine, 12, 15, 8. What comes next? 21, exactly. And then 24. It's a sequence of numbers that increase by addition. And so I could write this using the symbolic formula. Y equals 3x plus 6. All right, that's exactly the formula that will build this arithmetic sequence. When x is 0, we're at 6. Even though I don't see it in my table, that's okay. When x is 1, we're at 9. When x is 2, we're at 12, etc. And if I wanted to write it as a sequence, I would say a sub n equals 3n plus 6. Where now a sub n, pronounce a sub n, is the y, and the n is the x, but there's no other difference. It's just a linear function where instead of calling it x, we call it n. And instead of calling it y, we call it a sub n. So a lot of the exercises involved with sequences is, here's the first four terms, figure out the next one. Or here's the first four terms, figure out a formula. Or here's a formula, what are the terms going to be? But it's all about a numeric representation of a linear function and a symbolic representation of that same linear function. Geometric sequences if I said X and Y, and I had, let's see. Three, 6, 12, 24. That right there is a geometric sequence. 3, 6, 12, 24. Well, what comes next?
48.
48, exactly. Because what am I doing? I'm multiplying by 2 each time. So if I were to write this as a formula, I would say y equals, it would end up being, hold on. Wait. Yeah. Apparently it's been a while since I did exponentials. Y equals 1.5 times 2 to the x. I'm going to write this on another page. That's too many mistakes. Start over. The example. Geometric sequence. Three, 6, 12, 24. That's the geometric sequence right there. 3, 6, 12, 24. The next term would be 48 because we're multiplying by 2 each time. And I could write it as y equals 1.5 times 2 to the x. So I could write that as an equals 1.5 times 2 to the n. The other thing you can do with sequences is you can think about them not in terms of what does n give you, but what is the next term. So notice each subsequent term is 2 times the previous. That's exactly what an exponential function does. You multiply by 2 each time. So a sub n plus 1 is just going to be 2 times a sub n. Each subsequent term is 2 times the next one. And the very first term is 3. If I want to find the 16th term, I need to know the 15th term and I double it. In order to find the 15th term, I needed to know the 14th term, which I've doubled. And I work all the way back until the first term was 3, and I can get as far as I need just by doubling every single time. So these 3 representations are mathematically identical. They're just slightly different ways of writing it. And there are times when thinking about things in terms of sequences is more useful. Times when thinking about them as functions is more useful. And if you continue in math, that's awesome. You're not going to touch this again until you get to math 253, which is why this is all I'm going to say about this right now. Okay. So.
I have one question.
Yeah.
You know, like when you're graphing, you make a table of values, X and Y's. Are those values in relation to a sequence? I mean, you can't figure out, you can't.
Pretty much. Sometimes if the next term is a simple mathematical function of the previous term.
Then you can.
So let me give you a super interesting sequence. So this is the Mandelbrot set. Oh, it's going to give us a video. Cool. And it's built through sequences. It's built through a very simple mathematical operation that says take your number, subtract 3, and square it, basically. And just keep doing that and doing that and doing that. And then that number is probably going to get bigger and bigger and bigger in that sequence. If that sequence blows up to an infinitely large number, you make that point black. Actually, no, if it stabilizes, you make that point black. If it blows up, you give it a color. And so this really kind of trippy, beautiful picture, which notice repeats itself as you get smaller and smaller. This whole thing, which covers the whole dimensional plane, is built from a very simple mathematical operation, the same one that you just do again and again and again. Just like this sequence here is built by a very simple mathematical operation that you do again and again and again. You add 3 each time, and this one is you multiply by 2 each time. And so even very simple mathematical sequences can give you very interesting results. Yeah, good question. All right. So that brings us to section 5.4, dimensional analysis. This, or as I like to call it, changing units. How many inches are in a foot? 12, great. So you'd say 12 inches for 1 foot. That's a good start. Frida is 5.5 feet tall. How many inches tall is Frida?
Proportional, right?
Yeah, how would we answer that question? I give you a measurement in feet and I want a measurement in inches. So how do I do that? Any ideas? Yeah, multiply. What do I multiply by? I multiply by 12. 12 times 5.5. This you could call a conversion factor. And most of me, all of us would just do this and we'd get 66 inches. But I want to slow it down a little bit because this is the super simplest version of dimensional analysis. So instead, what we're going to do is we're going to do 5.5 feet times 12 inches per 1 foot or 1 feet. We have to keep the units the same. And then just like numbers, we get to cancel units. And we end up with 5.5 over 1 times 12 inches, which is 66, and then our units are inches. The key with dimensional analysis is just to write your units and your conversion factors, and it's all about multiplication. Usually ends up being a long string of multiplication when you get into a more complicated conversion, units converting. So let's ask how many centimeters tall is Frida? And I can tell you the conversion factor is 2.5 centimeters per inch. Hard to do conversions if you don't know the conversion factor. So that's part of your job when you're doing these changes. So let's forget the fact that I know it's 66 inches and let's start with 5.5. What are the units on the 5.5?
Those are feet.
Feet, okay. And I want to convert that, but I don't have a feet to centimeters conversion. But I do have an inch, a feet to inches conversion. And I have a centimeters to inches conversion. And so I just list all those conversion factors out one after the other. And then I start doing some cancellations. Aha, that feet cancels with that feet. That inches cancels with that inches. Leaving me 5.5 times 12 times 2.54 centimeters. That's the units I'm left with. And that's going to be exactly the number I'm looking for. That's what calculators are for. 167, technically 0.64 centimeters, but that's not a lot of distance. That's the amount a person's height changes over the course of the day when they're standing a lot. So probably would end up rounding that to 167 centimeters. The reason it's called dimensional analysis is often we work in more than one dimension. This were examples of a single dimension, height or length. But what if I want to say how many cubic inches, AKA inches cubed, are in a cubic yard? So I'm converting from yards to inches. You may know how many inches in a yard, but let's pretend we don't. Let's use the following conversion factors. There are 3 feet for 1 yard, and there are 12 inches to 1 foot. So we've got a cubic yard. How many of those is that then? That's 1, right? So that's got 1 yard cubed. And we want to convert that to inches. So we're going to multiply it by 3 feet per 1 yard. But wait a minute, it's a yard cubed. So is multiplying it by 3 feet per 1 yard going to do the trick? No, I have to do it 3 times. Because yard cubed means yard times yard times yard. That will allow me to cancel the yard cubed with all of those. I'm going to rewrite so we have space. 1 yard cubed times 3 feet per yard times 3 feet per yard times 3 feet per yard. Cool. That'll allow me to get it from cubic yards to cubic feet, but I need to get it to inches. Well, there are 12 inches per foot, but how many feet units do I have to take care of? I have to do it 3 times. So I just list it 3 times. once I get them all listed out, yard cubed is yard times yard times yard. So that yard cube will cancel with those 3 yards in the bottom. And then each of these feet will cancel with each of those feet in the bottom, leaving me in inches cubed, which is what I want. So I end up getting 1 times 3 times 3 times 3 times 12 times 12 times 12 inches cubed. $46,656. 46,656 cubic inches in a cubic yard. That's a lot. That's the other thing to keep in mind with dimensional analysis is your numbers can get pretty big pretty fast. Right? Once you work in greater than 1 dimension. We're not really going to work in 4 dimensions or higher very often because that's not something we have to deal with, but we can certainly get up to 3 dimensions. All right. The last idea is, so far we've talked about simple unit measurements, a foot or a cubic yard or a centimeter, but there are also unit measurements that are a little more complicated, like miles per hour and feet per second. If you were measuring the speed of a car, which one of these would you, which units would you want to use probably? Miles per hour, I saw Sean say that. If you were measuring your walking speed, which one of these would you probably want to use?
The
Feet per second, yeah, right?
metric.
Yeah, or let's say like a bowling ball rolling. Right, we're not going to measure miles per hour for a bowling ball because a bowling ball is never going to go more than about 100 feet, which is a very small fraction. Right, we could talk about miles per second. Why would we ever do that? Well, I guess if we're talking about like a rocket or a planet. We could talk about feet per hour. And you're probably going to be talking about like a snail or something. So there are common units that we use often. And every once in a while, we want to convert from one to the other. So let's convert 12 miles per hour to feet per second. And to do this, we just need our conversion factors. Is that what I called it? Our conversion factors. So I'm going to start listing some. There are 5,280 feet in 1 mile. These are all things that I'll give you. If I'm asking you to do this without the use of the internet, by the way, oh, we're done. All right, so technology is great. I still want you to understand what's going on underneath it, so I'm still going to put it on a test. But you know, Google will tell you every time. And in fact, it gives you an approximate multiplication. If you want a detailed version, you can go to an AI. If you want to use your phone, most phones have, and I've been using this recently. I climbed way up Mount Hood the other day and I wanted to get above 9,000 feet, and my GPS had the inclination meters. So I had to convert meters to feet. And if you go to most calculators, mine has a little ruler right here. And now I can, 2,440 meters is about 8,000 feet, right? So You're not going to be doing this by hand very often, but it's important to understand why. So anyway, our conversion factors. We can convert feet to miles. Maybe I don't know how many seconds are in an hour, but I definitely know there are 60 seconds in 1 minute. And I definitely know there are 60 minutes in 1 hour. So I've got 12 miles per hour, and I need to get those into feet per second. So I have to cancel out somehow the miles. So I'll cancel that out by doing 5,280 feet per mile. That will cancel the miles. And I also have to cancel out the hours. So I have to do this actually backwards. 1 minute is going to be 60 seconds. Sorry, let me see. 1 hour, let's do that. It's going to be 60 minutes. And then 1 minute is going to be 60 seconds. I flipped these conversion factors because the hour was in the bottom, so I needed to flip them. So one of the things to do when you do this by hand is to keep track of which of your conversion factors is it going to be flipped or not. Sometimes you have to flip it because nobody gives you a conversion factor and says there's 1 minute per 60 seconds. They just don't do that. They say there's 60 seconds in a minute. Okay, so let's check our units. There's miles and miles that cancel. There's hours and hours that cancel. There's minutes and minutes that cancels, which leaves us with feet per second. Great. And now we just have to do the numbers multiplication. 12 times 5,280 divided by 60 times 60 equals 17.6 feet per second. The 12 miles per hour is a fast run for non-Olympic sprinters, right? So if they have to cover 100 feet, how many seconds will that take? Which is maybe a question you're going to answer more often. How long will it take to run 100 feet at 12 miles per hour? So we convert this to how long will it take to run? And by how long, I mean, I guess, how long in seconds? Because usually when we're talking about sprinting, we're talking about seconds. How long in seconds will it take to run 100 feet at 17.6 feet per second? Distance equals rate times time. 100 feet equals 17.6 feet per second times the number of seconds. So 100 over 17.6 equals 5.7 seconds, approximately. And that's dimensional analysis. It's just converting one unit to another unit often so that you can answer a question in units that where it makes sense. I don't want to know how many hours it's going to take someone to run 100 feet if they run 12 miles per hour. That doesn't make any sense. And I'm also not going to ask how many seconds will it take a person to run 0.0189 miles, which is what 100 feet is. Right, we ask questions using certain units, but we often answer them using other units. Dimensional analysis was what allows us to change those units. Okay. Um.
I put one question on here that involves circles. Because circles are one of those places where we often have to change units. Yeah, just show me what those are. I'll take the grade, but one of those is I don't know, 14.4, sheet 5. Okay, I'll update that right now and also that. All right, now that we have a larger group though, I am gonna talk through the format for the final again. And I'll start writing my